Good morning, everyone. We had been discussing about accuracy and precision, and this is the second session. In the first session, we dealt with the definition of error and how they are numerically expressed in terms of absolute error and relative error. Then we did practice some numericals related to it. We also had a view about how the errors are being classified into two main types. They are determinate error, indeterminate error. Determinate error being further classified on the basis of their source or on the basis of their sample size into the following classification. So today we will be looking into a little bit details about all these classification, what they are, a little bit detail. So that is what we will be looking into in the today's session. So let's start with the determinate error, the first type. Determinate error can also be called as systematic errors. Okay, so they, as we already discussed, their source is known. So whenever we say any analytical determination is having determinate error, we actually know the source from which the error is coming. Another characteristic of determinate error is they are unidirectional with respect to accepted value. That is, the measurements are closer to the accepted value with a plus and minus error. That means often the error that is coming in the because of determinate error would be lying closer to the accepted value. Only thing that they would be showing little bit deviation from it, which can be represented as a plus and minus error in the analytical determination. Another thing that was noted down is that they are reproducible. Obviously, if the source is the same in all the analytical determination, then that means those errors will continue to happen till the source is corrected. Further, this part we already discussed when we talked about whether they can be corrected or not. Obviously, since we know the source, we can definitely correct or avoid these kind of errors. Sometimes in the analytical determination, it is not able to be avoided or corrected. So in those cases, at least by some changes in our practice, probably we can minimize these kind of determinate errors. Now, types of determinate error on the basis of source. This we discussed, we just looked into in the classification. So the first type of error that is based on the source is the instrument error. So instrument error, as you can see, is as a result of certain imperfections that are coming in the measuring device. Whatever measuring device you are using for analytical determination, any error in that instrument can lead to instrument based error. So for example, you are doing like measuring of volume using graduated glasswares like burette or measuring cylinder. These apparatus you use for measuring volume, usually in your practical classes. So the error in the graduation, I mean to say graduation means the marking on the glasswares, can also lead to error in the volume. Another error that can like the graduation on the glasswares can be affected is that when you dry it in an oven, suppose you wash the glassware and dry it in the oven, and then you take out after constant washing and heating and drying, these glasswares show some kind of expansion or contraction, leading to the slight changes in the graduations on the glassware. Apart from that, if you are buying a very low grade quality, the graduation can obviously be not perfect in its authenticity. So glassware based graduation errors can definitely happen, which can lead to error in the volumes that are measured in any kind of analytical determination. Suppose you are using certain kind of electrical instruments, they are also prone to errors, because suppose your power supply is having some fluctuations, then definitely these electrical instruments you are using for any analytical determination would show a certain kind of error. Apart from that, there are resistance coil in these instruments, so there can be errors based on increase in resistance or decrease in resistance that are happening inside the instrument while they are being continuously used. So all these kinds of errors that are arising as a result of the instrument that you're using for the measurement of any kind of analytical determination, they are all categorized under the category of instrument error. Second type of determinate error based on source is the method error. So method error is basically, as the name suggests, is as a result of any kind of flaws in the method that are used for any kind of analytical determination. So in the methods we use different kinds of reagents, or if it is some kind of reaction, so it can be any procedure that you follow in a reaction. So any kind of non-ideal behavior in the solvents or the reactants or the reagents that are using, they can lead to these kind of method errors. Suppose if you're using any organic reaction and you're trying to find out the rate at which the rate of the reaction, then obviously that rate would be affected by certain side reaction that is happening, or because of non-ideal behavior of the reactants. So all these factors can affect the cause the error in the measurement of the rate. However, these errors are kind of inherent. They are kind of born in the system. So we know that this is coming as a result of method error, but we since these are inherent in the system, we actually cannot easily detect them or correct them. So though here in the method error we know that this error is coming from method, we cannot pinpoint the inherent nature of that error, like from where exactly we cannot pinpoint. And since these are inherent in the reactant, it's the behavior of the reactant or it's the behavior of the reaction that is leading to this kind of error, we cannot remove it because it is the nature of the reactant or it's the nature of the reaction that is undergoing this particular reaction. So these are inherent, they are their natural, they are their natural tendency. So we cannot therefore easily sometimes detect them, or even if we detect them, we usually cannot correct them. Now how can you avoid these type of errors? Probably you can change the methodology, thereby you can do some kind of improvement. But as such, these method errors usually are inherent and they will be there. Only thing is you can say that these errors that are coming might be because of the method error. Then the third kind of determinate error based on source is the personal error. This, as the word suggests, it's because of the erratic personal judgment, as also from prejudice and bias. Now, what do you mean by is the erratic term? The erratic term means it is the lack of consistency. Okay, there is no orderliness, there is no a kind of disciplined pattern in taking up the analytical determination. Often there is a lot of biasing involved in the measurement. This you might have also come across while you are doing the volumetric titrations. Whenever you do the volumetric titration, often what happens is that when you have to do repetitive titration, you have a inward feeling that okay, this is the correct volume at which my endpoint is coming. Then you just focus all your attention on that particular value and you keep the volumetric titration in such a way that unknowingly you add excessive drops to make it to come to that volume, so that you ultimately get a uniform kind of measurement. This happens particularly in those titrations where the color is not very instant. There is a gradual change in color, like when you are using methyl orange. Okay, those titration has a gradual change in color. So those titrations you will be more drawn to kind of biasing. So that kind of errors are because of your personal error. So they can be corrected by a very disciplined pattern in which you take the measurement, so that you follow exactly the correct judgment, uniform way of doing the measurement. If you practice, then definitely these errors can be greatly minimized. Now, the second way in which the determinate error are classified is on the basis of sample size. First type is the constant error. So, constant error are usually independent of the size of the sample or the concentration of the analyte being used. For example, in volumetric titration, you add one drop extra to cause the color change. So this one drop that you add would be the same whether you are doing 10 ml volume of the analyte or you are using 20 ml of the analyte. So this excessive drop that you are adding for seeing the change in color would be the same in both these volumes. So that is why this kind of error, this excess error that is coming, is size independent. That is, it doesn't depend upon the size of the sample that you are measuring. These kind of error becomes significant when the sample size is small. That is because if suppose you calculate the error, suppose the volume of the one drop that you are adding is 0.01 ml. Then if you calculate the error in 10 ml and 20 ml, the error in the 20 ml, percentage of error in the 10 ml would be a little bit higher. How can you calculate that? Suppose the volume is 0.01 ml, so 0.01 divided by 10 into 100, when you do, you will get a value. Similarly, you do 0.01 into divided by 20 into 100. If you do, you get the value. The value that you get for the 10 ml would be a little bit higher. Let's calculate that probably. Let me do it in my calculator. So it comes out to be 0.01 divided by 10 multiplied by 100. You get, for the 10 ml, you are getting 0.1 percentage error. Now let's look the error for the 20 ml. So 0.01 divided by 20 multiplied by 100, it is 0.05. The error for 10 ml is 0.1 ml, 0.1 percentage, and for 20 ml it's 0.05. So error for 10 ml would be higher in comparison to error for a 20 ml. So that is what I'm saying. So as you reduce the size of the analyte that is being measured, what you get is that you have the constant error, the ratio would be a little bit higher. So it becomes significant when you reduce the sample size. If suppose you plot a graph between the error and the sample size, the constant error would be a kind of constant line. It would be something like that because it's independent of the sample size. Second type of error is the proportional error. These decrease or increase in proportion to size of the sample. So that means this is dependent on the size of the sample. So that is what you see here in the curve. This is the proportional error. You see that as the sample size is increasing, you have a increase in the graph. So this arises because of certain kind of impurity that is present in the analyte. Suppose you are analyzing the amount of copper and that particular solution has Fe3 plus as impurity. So as you double the sample size, you obviously are going to double the amount of impurity in the analyte that you are measuring. So this impurity thing is what is leading to the proportional error in this particular error. And another thing is these a fraction of impurity is irrespective of the sample size. That means the percentage of impurity that you would be measuring for a 10-gram sample or for a 20-gram sample would be the same. Okay, so the fraction of impurity will remain the same, but if you in general look into the error in not in terms of percentage, but if in times of just a real numerical value, then as you increase the sample size, you will have still an increased error that you are going to see. So that is how the graph of these constant and proportional error looks like. Now, apart from determinate error, we have another kind of error which is called indeterminate error. They also are called as random error. Just be aware of these terms. Like determinate error, as I told you before, it also called as in systematic error. In the same way, indeterminate error can also be called as random error. So as this is the first thing that we discussed there, the sources are known. So obviously, you cannot know from where this error is coming. Inevitable uncertainties associated with any measurement. So any kind of measurement, these errors are inevitable. They definitely will come because we don't know the source, and these errors are like coming like that. Lead to random fluctuation around the mean of a set of measurement. This you might have seen, like whenever you do a set of measurements, like in physical chemistry, whenever I don't know whether you have done it or not, probably you'll be doing this year. When you do any kind of physical measurements, you will see that the same measurements, when you do, the values are kind of fluctuating across a mean value. So this kind of graph would look like a Gaussian curve. Okay, so like you have the measurement values plotted in the x-axis, and if you see the occurrence at which these values are coming, when you measure it, this curve will look like a Gaussian curve, a bell-shaped curve that you are going to see here. So here, the values that are coming would be kind of fluctuating across the mean value. So this is how the graph of coming as a result of indeterminate or random errors look like actually. So this is all about the different types of error that we are going to look into. Just before I finish this up, I would like to just ask you a question which you would be answering me in the live session. Consider these two measurements that are made of the percentage of lead in a sample of brass. These are the two sets of measurement done by two different people. I'm asking you a question. Which of these two sets contained the most precise measurement? So look into this and try to answer it, and we will see the answer to it and try to learn more about precision in that particular session. Thank you very much for your attention.